We've already practiced looking at triangles or acute triangles and determining the 6 trigonometric functions of angles that we see within an acute triangle. My graph A right here represents one of those where we have an acute triangle and then we determined its 6 trigonometric functions based on that acute angle. However, we can extend this a little bit further by noticing that in examples B, C, and D, we can make that sweep of that angle greater than 90 degrees so that one, it lands in the second quadrant or the third quadrant or the fourth quadrant, but we can still look at their 6 trigonometric functions and their identities and come up with what those sines and cosines and tangents and so forth are. So we're going to look at a couple examples of how can we identify what the sine of an angle is where the angle is greater than 90 degrees. So in this example, notice that our angle is swept across into the third quadrant. So my theta extends beyond 180 degrees but less than 270 degrees. I have a point that I'm able to recognize as a point -3 and -5. So I would like to find out is, well, what are the 6 trigonometric functions of theta, even though theta is greater than what we call an acute angle? So we have our functions over here. The first thing we need to do is identify r, the radius at this particular point. And if we remember, radius equaled the square root of x squared plus y squared. So x in this case is the -3, that's the x value. So I would have a -3 squared plus the y is a -5, so a -5 squared. And I would take the square root of that. So that would be a 9 plus a 25, square root of 34 is what r is. From there, it's just plugging in and identifying the values that we have. So if we wanted to find the sine of this theta, this particular angle, we'll notice that it is the value, the y value, which is a -5, over root 34. Which is the radius. And then we would need to rationalize the denominator as well. So let's multiply both sides by a root, or top and bottom, by a clever version of 1, which is a root 34. Then my sine of theta would be -5 root 34 all over 34. And that's the sine of theta. From there, let's go ahead and determine what the cosine of theta is. And I think it's going to be a similar process here. Cosine of theta, that's my x value over my radius. My x value is a -3. R is a root 34. Clever version of 1 to rationalize the denominator as well. And that equals -3 root 34 over 34. So therefore, we've already found the sine of theta and the cosine of theta. Something that might be of interest to us right now is notice that both of these are defined at any time, at any point. The sine and the cosine is always defined as long as my radius is greater than 0. And obviously my radius is going to be greater than 0, or I just have a point. But good to note that sine and cosine are available or are defined at any values of x and y. That's not true with everything else. For example, our tangent of theta. In this case is my y value over my x value. My y is a -5 over a -3, and that produces a 5/3. So it's defined there, but it's not defined if my x value was a 0. Let's look at cosecant. Let's see if we can fit the other 3 on here. Cosecant of theta is my r value, which we discovered is root 34, over my y value, which is a -5, and I'll put the negative out in front. So cosecant is -root 3405, and that's defined again where y does not equal 0. If we want to look at the secant as well, that is my r value, my radius, over my x value, and my x value is a -3. And I'll put the negative out in front. Then lastly, the cotangent. Cotangent of theta is my x over my y, or my reciprocal of my tangent. So I have a -3 over a -5, and that simplifies to 3/5. So the point of this example is to remind us, or to demonstrate to us or teach us, that we can find the 6 trigonometric identities: sine, cosine, tangent, cosecant, secant, and cotangent of angles that are greater than 90 degrees. Another idea that's important as we explore the different functions is what happens when our angle lies on or produces the terminal side on an axis. And those are called quadrantal angles. So in this example, notice that I have a line that's on the x-axis. And for example, let's see if we can find out the sine and tangent of the angle that's produced by a line that's on the x-axis. So what's the angle? What's the measurement of the angle? Well, we know the measurement of the angle is 0 degrees. And that's in degree world. In radian world, it's just 0. So how would we find the sine and tangent as example of those? Well, we're going to choose a point on the line to begin with. A great point to choose is a point 1. Remember, it doesn't matter how far out the line goes or where we choose a point, the angle doesn't change. And that's what we're trying to determine is the angle, or that's what we're using is that particular angle. So let's choose a radius of 1 unit. And from there, the sine of 0 degrees in degree world is the same thing as the sine of 0 in radian world, which equals my y over my r. And my y in this particular case is my up or down at this particular point, and my height is 0 with a radius of 1, and that just equals a 0. So the sine of 0 degrees or the sine of 0 radian is 0. Then let's look at the tangent function as well. So the tangent of 0 degrees, same thing as the tangent of 0 radian, and the formula for that was my y over my x. My y value over my x value, which in this case is 0 over 1, and equals a 0. So both my sine and my tangent functions are 0 when I have 0 degrees as my theta. The next quadrantal angle is where we have an angle measurement of 90 degrees in degree world, and then in radian world, it is pi halves radian. That's where we have a straight, or that terminal angle is vertical along the y-axis. So we want to explore that. So let's explore again the sine and tangent function, see what happens if we choose a particular point of a radius. We'll choose 1, again, because it's a great number to choose. And then we're going to work with a theta that's 90 degrees or pi halves, depending on what world we're in. So the sine, excuse me, so the sine of theta in this particular case was 90 degrees, or the sine of pi halves. Both of those should produce the same result. One's in degree world, one is in radian world, but they should produce the same result when we're looking at the sine. And so that equals, sine again was defined as my y value over my r. My y value, notice that my point is 0 and 1. So my y value is a 1, and my r value is also a 1. So the sine of 90 degrees is 1, or the sine of pi halves is 1. Then again, as a comparison, let's look at the tangent function. The tangent at 90 degrees, or it can be written as the tangent at pi halves, again from degree world or radian world. We want to know what is the ratio of those two lengths. What's the ratio of my y versus my x? That's what tangent means. Same thing with sine. Sine's a ratio of two sides of a triangle. So the ratio at 90 degrees is my y value, which is a 1, over my x value. That's what tangent is talking about, the ratio of 1 to 0. And that is undefined, obviously, because you cannot divide by 0. So I have an undefined, however I want to write that, I don't know. Yeah, that's probably not this way. We'll just say it's undefined, or my tangent at 90 degrees is undefined. This quadrantal quadrantal, can't say that word, can you? This quadrantal angle that we're looking at now is 180 degrees. So theta, 180 degrees, or in radian world, pi, radians. Let's choose a point. We're going to choose a point -1 and 0 so that we have a radius of equaling 1. So let's see what the sine and tangent functions look like in this particular case. So the sine of 180 degrees equals the sine of pi in radian world. And based on our identities that we have here, that's my y value over my radius. My y value is how far up or down it goes, is a 0. My radius is a 1. My radius is a 1. And so the sine of 180 degrees is 0. Let's look at a tangent of 180 degrees. The same thing as the tangent of pi radian. And that was my y value over my x value. And so my y value is a 0 over my x value, which is a -1. And that simplifies and reduces down to 0. So the sine and tangent of 180 degrees are both 0. And the last quadrantal angle that we want to look at is where the angle is swept out by 270 degrees, or 3/2 pi radian. So the sine, again, as an example of just looking at one of those, the sine of 270 degrees also equals the sine of 3/2 pi radians is my y over my r value. My point that I chose is a point 0, -1. The reason we chose that point was simply because it gave us a radius unit of 1 unit. If we chose another number, that would be fine too, but we just want to choose 1 as a radius unit. So our y value was a -1, and our radius, in this particular case, is a 1. So I would have a sine of 270 degrees equals -1. -1 over my radius, which is equal to 1. All right, let's look at a value of our tangent at 270 degrees. The same thing as a tangent of 3/2 pi. We again look at that. That's my y value over my x, or my ratios of my y's to my x's. At that particular case, the ratio at that point is -1 over 0. And as we discovered before, at 90 degrees, that's undefined. Be kind of curious if you want, just why don't you see if you can find the tangent of 270 degrees in your calculator, or the tangent of 90 degrees, and see what happens at that particular case. All right, point of this expressions, or the segment, was to let us know that we can find the sine, cosine, tangent, cosecant, secant, and cotangent of angles greater than 90 degrees.